Good day, class. So we will start today with liquid extraction. This is our, if I'm not mistaken, this is already our fourth topic in separation processes. Now, liquid extraction, or simply solvent extraction, or extraction as it is referred to in unit operations, is another separation process wherein we are contacting two liquid phases, and as such it is called liquid extraction. Now, this is a process for separating the components of a liquid, and that liquid is the feed, by contacting it with the second liquid phase, which is the solvent, with the two phases being chemically different. So it's a requirement in liquid extraction that our contacted phases should be chemically different. Now, the transfer of components in the separation process from one phase to the other is driven by a deviation from what we call thermodynamic equilibrium. So, if this thermodynamic equilibrium is not yet reached, then there will be mass transfer between these two phases. Now, separation is according to the difference in physical and chemical properties, one of which are the differences in polarity, and another one is their hydrophobic or hydrophilic character. So one must be hydrophobic, the other one must be hydrophilic. I'm referring to the phases. So these phases should not be chemically the same. So as such, in terms of their characteristics and properties, they should not be also the same. Now, the contacting of these two liquid phases produces another two phases, and they are the extract phase and the raffinate phase. So, the solvent-rich stream is the extract, and the portion other than that, or the other liquid stream that is being produced, is the raffinate. Now, in liquid extraction, we are more concerned, or we are more interested in the extract, because this is where the component from the feed is transferred to, and that is our extract phase. The raffinate is the, shall we say, the waste stream, or the byproduct, wherein we're not really interested because the component is not on it, or a majority of the component in the feed is not on it. So it's actually on the extract. Now, as to specific application of extraction, so it could be applied in the removal of acetic acid from water, and the removal is to the use of organic solvents. Now, in this case, distillation can also be used, but in some cases, they prefer to use extraction because distillation is highly energy extensive in terms of use. So, a lot of resources is utilized in distillation, whereas in liquid extraction, you only need to have a liquid that has the particular component that will extract from the feed your interested component on. So that is why liquid extraction is the one that is favored in this case, removal of acetic acid from water. Now, another one is in the removal of high molecular weight fatty acids from vegetable oil using propane as solvents. So when we remove these acids from vegetable oil, we are using either liquid extraction, or another alternative is the high vacuum distillation. Again, this one, if ordinary distillation could be used, this one is more even energy extensive in terms of use. So they'd rather go to using liquid extraction in this case. So the first application here, we're trying to remove a contaminant, that is acetic acid. And in the second example here, in the application, we are trying to recover a desired component, which is the fatty acid from vegetable oil. Now, another set of application would be the separation of penicillin from complex fermentation mixtures. So in here, we're trying to recover a desired component, which is penicillin, after it has been produced in the process of fermentation. Now, another in the removal of contaminant, as an example, is in the treatment or in the extraction of precious metals in mined ores. So, metal separation of aqueous solutions of copper, iron, uranium, vanadium, or tantalum columbium mixture. So either you're interested only with copper or you're interested in both, but you're trying to separate, let's say, copper from iron. So you can use liquid extraction for that. The same thing with uranium and vanadium and the tantalum columbium samples here. So these examples of separating these metal mixtures in aqueous solution uses a process of liquid extraction. In some instances, it's actually using what we call high pressure acid leaching in terms of taking away precious metals from ores that are being mined. Now you can read more on the application of liquid extraction in this section of your handbook. This is section 15-7 to 10 of your handbook. So please read on more applications on the topic of liquid extraction. Now there are two main classes of solvent extraction equipment. So it could be a simple case of a vessel with mechanical agitation, so a tank which has a stirrer on it, and it could be a vessel in which mixing is done by the flow of fluids themselves. So through the velocity differences of the phases that are being contacted, mixing occurs. So the one that initiates the mixing is the velocity differences of these flowing fluids inside the vessel. So there could only be two classes of equipment for liquid extraction, but in this particular class here, in the second one, there are several types depending on its design in terms of the objective of that particular equipment or in terms of the feed that it is to handle. Now let's go to definition of terms of in terms of extraction before we even go to material balances related to calculations in the design of the equipment, appropriate equipment, which will facilitate the extraction process. So when we speak of the feed in here in extraction, that is the solution that contains the component or components to be separated. It's liquid. Okay, so in it you have the feed solvent or the carrier solvent, and you have the solute. Now which of the two is the solute? So if you're given a decomposition of your feed, the one that is lesser in amount in terms of percentage composition or concentration, the one that is lesser in amount is your solute. The rest are referred to as the feed solvent or the carrier solvent, so because it's the major liquid component or components in the feed. So take note, your feed is composed of the solute and the carrier solvent or the feed solvent. Then we have what we call extraction solvent or separating agent. So we have a carrier solvent in the feed, but we also have another solvent which is the extraction solvent or separating agent. I think the name itself implies what it does. So this is the immiscible or partially miscible liquid that is being added to the process to create a second liquid phase for the purpose of extracting one or more solutes from the feed. So this is the primary thing why extraction happens. It's because of the extraction solvent. It is being added into the feed, that way it will be able to separate the component or components present on it. So it's the extraction solvent. It's different from the carrier solvent of the solute in the feed or separating agent. Extraction solvent or separating agent. Now, if the feed has two components, and that's the solute and the carrier solvent, we also have basically only two components in the separating agent or in the extraction solvent. These two components are the extractant and the diluent. The extractant is that main component in your extraction solvent that is primarily responsible for extracting the component from the feed that you are interested in. That's the extractant. It is dissolved in the liquid diluent. The liquid diluent here in your extraction solvent is equivalent to the carrier solvent in the feed. But in some cases, class, there is a third component that is being added in the extraction solvent, which is the modifier. So it may be added to increase the solubility of the extractant or otherwise enhance the effectiveness of the extractant. Meaning, the modifier will improve the percent recovery of your extractant, the manner in which it extracts the component from the feed that you are interested in. So it improves it by increasing its solubility in the extractant, or shall we say, it enhances the effectiveness of the extractant in your extraction solvent to take the component of interest from the feed. And that is our modifier. But in most cases, our separating agent, our extraction solvent, is only composed of the extractant and the diluent. Now, in here, in extraction, we also have what we call as the equilibrium stage or the theoretical stage. Our specifically in vessels, in vertical vessels or columns where extraction happens, we have these stages also. They are normally operated in multi-stage fashion. I'm referring to this column. So, what's a theoretical stage or equilibrium stage in relation to these equipments? So, it's a device or combination of devices that accomplishes the effect of intimately mixing two liquid phases until equilibrium concentrations are reached, then physically separating the two phases into clear layers. So, the equipment where equilibrium is reached is this particular theoretical or equilibrium stage devices if we have a multi-stage system. So the liquid are the feed and the extraction solvent are contacted in this particular equipment, and then after they have reached equilibrium, the two layers that performed, layers which are referred to as the raffinate and the extract layers are formed, they are being separated. So the one that facilitate that is the device we call the equilibrium stage or the theoretical stage. Now, we have this what we call extraction factor, and it's found in equation 15-11 in your handbook, section 15-22. If I'm not mistaken, this is still based on the 8th edition. So please, if you are using the 9th edition, just look for its equivalent there in your edition of your handbook. Now, the extraction factor is the ratio of the slope of the equilibrium line with the slope of the operating line. That is if you're going to look at it in a graphical manner or sense. Now, but if you're going to theoretically only analytically, shall we say, understand what extraction factor is, then it's simply the flow rate of the feed divided by the flow rate of the solvent. That is if its treatment is not in the pure graphical sense. So that's the extraction factor. Flow rate of the feed to flow rate of the solvent. We have also what we call the separation factor. It's equation 15-14, section 15-23 of your handbook. If we have relative volatility in distillation, this is its equivalent in extraction, and that is the separation factor. The greater the separation factor, the easy way it is to separate the components in our feed. So it is easier to separate components if this one has a big value or a large value. Now, we have partition ratio, distribution constant, or distribution coefficient, all of which can be represented by capital letter K. Now, in most books, this is referred to as the distribution coefficient. But in some other books, it's also referred to as partition ratio or distribution constant. Now, what is this K? And it's being used in determining the degree of extraction of a particular equipment or the efficiency of a particular equipment to facilitate separation of the components in the feed. Okay, this is the solute concentration in the extract phase divided by that in the raffinate phase after equilibrium is attained in a single stage contacting. So later on in this slide, you will know how to represent the concentration in the extract and the concentration in the raffinate. The same thing with the concentration in the feed and the concentration in the solvent. So in determining the distribution coefficient, this is simply the ratio at equilibrium of the concentration of the extract to that of the raffinate. Concentration of what? Concentration of the component we are interested in. So let's say component A. What is the concentration of component A in the extract divided by the concentration in the raffinate at equilibrium, and that is our distribution coefficient. Now, for the Lute systems with straight equilibrium lines, the partition ratio is equal to the slope of the equilibrium line. So, if your system is very dilute, meaning the composition of the component you are to separate from the feed is less than 10% or even less than 5%, the equilibrium line is a straight line. So, it's equal to the slope of that particular line. The K is equal to the slope of that particular equilibrium line. Okay, you can read on the partition ratio or the distribution coefficient in these sections of your handbook. And this table gives you the different distribution coefficient for different substances when present in the feed wherein it is to be separated from. So kindly look on this section of your handbook for this topic on partition ratio or distribution coefficient. Now we have also what we call as the loading capacity. Now this is the maximum concentration of solute the extract phase can hold before the two phases can no longer coexist or the solute is precipitating out as a separate phase. Now in the last phrase here wherein it says the solute precipitates as a separate phase, this is also already a case of what we call crystallization. So the maximum concentration of the solute in the extract wherein no crystallization yet is going to happen is what we call as the loading capacity. So no crystallization yet happens in this case. If it goes beyond this maximum concentration, your solute will precipitate as a separate phase. And that's the case already of crystallization. Now, this was mentioned in the previous slide. So this is how it's represented. So the concentration in the extract phase is Y. The concentration in the raffinate phase is X. So this is just a continuation of what's written there. So the concentration of component I at equilibrium in the extract and in the raffinate phase is your partition ratio or your distribution coefficient. Now, high partition ratios generally allow for low solvent use, meaning it will be economical because you will only be required to use a little amount of solvent, smaller and less costly extraction equipment utilization. In terms of the design of the equipment, it will be also smaller, and then it translates to lesser cost in constructing the said equipment and lower cost for solvent recovery and recycle. Now, during extraction class, it's seldom that the solvent is thrown or discarded at first use. What is being done in the extract phase, since the component of interest in the feed is being carried by the solvent in the extract phase, it will further undergo a physical separation process. So the solvent, the extractant, that is being separated from the component of interest from the feed that it carries. In that case, that recovery in here that is being referred to will be entailing lesser cost if partition ratio is high. So most of the solvents after being used are being recovered. They are not discarded. So they are recovered by another unit operation of separating the component from this particular solvent. And that process is solvent recovery and recycle. But it is not part already of this topic on liquid-liquid extraction. We will not discuss here anymore solvent recovery and recycle. But just take note that it is being done in the industries. The solvents are being recovered and recycled. Now, partition ratios on the order of 10 or higher are desired for an economical process. If in distillation it is suggested that relative volatility should be greater than 1 so that it would be easy to separate components in the feed. In extraction, it is desired that the value of the partition ratio is 10 or higher. That way, it would be economical to separate the solvent from the component of interest or the component that was extracted from the feed later on. Okay, so 10. So it's anyway a multiple of 1 in terms of 10. Now, okay. Then we have what we call the solute selectivity. I think this is also implied or as to what its purpose here. It is important not only to recover a desired solute from the feed, but also to separate it from other solutes present in the feed, and thereby achieving a degree of solute purification. The selectivity of a given solvent for solute I compared to solute J is characterized by the separation factor. Analogous to separation factor, again, analogous to the symbol that we're using in relative volatility in distillation. So take note, the separation factor. How selective is your particular solvent for a particular solute I? So it more or less tells you that its preference, how highly it prefers to extract only solute I if you have both I and J present in your feed. So that particular preference of that particular solvent to only extract I or separate I from J in your feed is the separation factor. And it is actually the ratio of the K's, the K of component I to the K of component J. What is this K? This is the partition ratio or the distribution coefficient that was discussed in the previous slide. So the ratio of this Ki and K sub j is your separation factor. A value much greater than 1 to achieve an increase in solute purity is the one that is preferred. So in this case, it's very similar to relative volatility. To ensure that your particular extractant will only prefer to take out component, let's say I, in a feed consisting of component I and J, you have to have a separation factor of 1.0 for these two. And that is, if the ratio of your partition ratios or distribution coefficients is greater than 1, then that could be done. And that would be easy, and it would be easy to separate later on component I from component J. So selectivity or something to do with the preference of the extractant to a particular component in your feed. Now, let's go to mutual solubility. So, it is desired that your solvent should have low liquid-liquid mutual solubility between itself and the feed. So, this is desirable because it reduces the separation requirements for removing solvents from the extract and raffinate stream. So meaning as much as possible, we want the solubility of our feed to the solvent phases to be low. So low liquid-liquid mutual solubility between the feed and solvent phases. That way, they should not be completely, let's say, they should not be completely miscible or soluble. That way, it would be easy to separate later on components. Okay, especially the solvent from the extract and the raffinate layer. So it should be low liquid-liquid mutual solubility. Stability has something to do with your solvent having little tendency to react with the product solute and form unwanted byproducts. We don't want any actually reaction to happen in pure liquid extraction. It's a simple physical process that should not have any chemical reaction occurring. So this is a requirement. Also, it should not react with feed components or even degrade to undesirable contaminants that may cause development of undesirable colors or odor over time, or cause difficulty achieving desired product purity, or even accumulate in the process because they are difficult to purge. That has something to do with your solvent stability. It should be stable, it should not react, it should not degrade. It should not, shall I say, form into undesirable contaminants in your equipment, inside your equipment. Then we have viscosity. There should be low viscosity in extraction, since higher viscosity generally increases mass transfer resistance and liquid-liquid phase separation difficulty. I think viscosity always is a hindrance to transfer. Whether it's mass transfer or heat transfer, viscosity is something to be considered on in terms of the properties of the phases that are being contacted, and it's also being considered here. So it's a requirement as much as possible that viscosity should be low. So an extraction process can be operated at elevated temperature where viscosity is significantly lowered for better mass transfer performance, even when this results in low partition ratio. Even if it will result in a low partition ratio for viscous feed, at times there's a need to operate your extraction equipment at elevated temperature, or shall I say normally higher than standard room temperature. That way, the difficulty of separating or the difficulty of transferring the mass of a solute from the feed to the solvent will be addressed. That is in the case of this property, which is viscosity. Then we have recoverability. And since we want to recover our solvent, so as it will be economical for the process, so your solvent should be recoverable. Okay? Then if we have considered viscosity, we also need to consider density difference here between the solvent and the feed phases. And this difference in the solvent density and to that of the feed should be on the range 0.1 to 0.3 grams per ml. This is the preferred range of difference for the density of the feed and the solvent. A value which is lower, meaning less than 0.1, makes for poor or slow liquid-liquid phase separation and may require use of a centrifuge, meaning it will take some time or the process of extraction will be very slow. And as such, there's a need to centrifuge your feed and your solvent in that case so that you can separate the two layers. Now, what about if higher than 0.3? In this range is the density of your solvent and your feed phases. So a value that is too high makes it difficult to build high dispersed droplet population density for good mass transfer. What does this mean? It's difficult to build high dispersed droplet population density. It is difficult to mix the two phases together and maintain high hold up of the dispersed phase within the extractor, but this depends on the viscosity of the continuous phase. Now, if the value for this difference in density between the solvent and the feed is greater than 0.3, let's say for example it's 0.5, it would be difficult to build this high dispersed droplet population. And there's this mention, and if it would be difficult to build this high dispersed droplet population density, it would be difficult for the two phases to mix. Now, there is this mention about the dispersed phase and the continuous phase. And in the design of your extraction equipment class, we are referring to the feed as the continuous phase and the dispersed phase is the solvent. But in some other cases, it's the other way around. It is the feed that is being dispersed while the solvent is the continuous phase. So we have to be very careful when we read the problem as to what it dictates us to consider as the dispersed phase or the continuous phase, because it really matters as to how big your extraction unit is if your feed was considered as the continuous phase or if it is considered to be the dispersed phase. So again, the dispersed phase most of the time is your solvent and your continuous phase is your feed. But in some other cases, it's the other way around. Your feed is the dispersed phase and your solvent excuse me, your solvent is the dispersed phase and your feed is the continuous phase. You just have to be able to get that particular information accurately in the problem. So we don't want a density difference higher than 0.3 because it's difficult for our feed and our solvent to mix. And that way the solvent will be able to take out the solute that we want to take out from the feed. Okay, so more on this liquid properties. Then safety solvents with low potential for fire and reactive chemistry hazards are preferred. Okay, so that safety is ensured. Then interfacial tension. This one we also determine or quantify in some cases if this interfacial tension is not given in the problem. And there's a way of doing that using an empirically determined equation. So preferred values for interfacial tension between the feed and the extraction solvent phase generally are in the range of 5 to 25 dyne per centimeter. Your 1 dyne per centimeter is equivalent to 0.001 Newton per meter. So this is again the range of value for interfacial tension uh, between the feed and extraction solvent. So 5 to 25 dyne per centimeter. If the value of the interfacial tension is lower than 5, your system, the feed and the solvent that is, will emulsify. What emulsify means here is that it will tend to form a colloidal mixture. This you learn in Chem 1, wherein there is this, shall we say, stable dispersed phase that will indefinitely not settle, and as such separation will be very difficult. So emulsification only happens in colloidal suspensions. In that case, your feed and your solvent here will tend to form that particular mixture, and we don't want that to happen. So as much as possible, we want our interfacial tension to be 5 or even higher. Now for systems which are very high, having high interfacial tension, probably greater than 25, the systems with higher values, the dispersed droplets tend to coalesce easily, resulting in low interfacial area and poor mass transfer performance unless mechanical agitation is used. Okay, so what happens to your dispersed droplets is they will tend to coalesce meaning they will form into lumps. If they will group together and form into lumps, then you decrease the interfacial area for mass transfer. If the interfacial area is decreased, then there will be a much lesser amount of transfer that will happen, or there will be poor mass transfer performance in that case. So to ensure that this will not happen for systems with interfacial tension higher than 25, mechanical agitation is made sure to be incorporated in the design of the extraction unit. So there has to be an agitator. That way, your dispersed droplets, whether it's your feed or your solvent, will not coalesce or coagulate, so that your mass transfer area will be increased. Now, industrial hygienes, the solvent with low mammalian toxicity and good warming properties are desired. So it should not be toxic to us living creatures. So that has something to do with mammalian toxicity. Now, with good warning properties, this has something to do with an indicative property of the solvent to tell you that something is really wrong. So probably in terms of its color, it will change, or in terms of the texture, or in terms of the scent, the smell. So it should have good warning properties to tell you that there's something wrong with it. So nonetheless, when solvents are bought for use in extraction, in terms of its properties, it's carefully being studied. That way, this will not happen, and even more so the toxicity part to us, to all living creatures, that is. Low toxicity and low dermal absorption, so it should not get easily absorbed in the skin, should reduce the potential for injury through acute exposure. So we don't want anybody in the plant to be exposed to something that is very toxic. So it's required that it should have low toxicity and it is not easily absorbed by the skin. So low dermal absorption. The freezing point is not a problem with us here in the Philippines because we don't have winter. But in the western part of the globe, they are considering this particular property of the solvent to freeze during cold season or during winter. So solvents that are liquids at all anticipated ambient temperature, meaning even at low temperatures, it's expected that the solvent that you are using there should be, shall I say, having low freezing point. Unless otherwise they really need to use such particular solvent, and if sometime it's not avoidable that it will freeze, then it is required that that particular solvent could be easily thawed, so it could be melted, that is. prior to it being used. Now, we want as much as possible that our solvent is recoverable and it will have different use. It will have multiple use after it was being already used in the process of extraction. So, if only it could be used in the other parts of the process. That way, again, it will address the concern about economy. So, multiple uses, it is desirable to use an extraction solvent, a material that can serve a number of purposes. Now, as for environmental requirements, these are more so to address the different environmental regulations given by the government as to later on in terms of the treatment of the waste product of this particular process using the solvent. So solvent must have physical or chemical properties that allow effective control of emissions from vents and other discharge streams. Meaning it would be easy for the environmental engineers or simply the engineers in the plants to have control of the emissions of these particular solvents. Now, preferred properties include low aquatic toxicity. Again, it should not be toxic, and low potential for fugitive emissions for leak or spills. What we mean with fugitive emission, it's easily for us to pinpoint in what particular location is the particular, shall I say, effluent or emission present. That way, it's easy to contain it. So, low potential for fugitive emission. A fugitive is a person which is very hard to get caught, or it's not easily caught. So, it's the same thing with emission here. It's simply referring to the containment of the emission should there be unexpected leaks. Okay? It is also desirable for the solvent to have low photoreactivity in the atmosphere and be biodegradable. I think this is a given almost for all processes, that the things that we're using should be biodegradable. They should not remain as is in the system wherever it is, and it should not persist in the environment. Now, materials of construction, as much as possible, we don't want to use a solvent that will require a material for our extraction unit that is very expensive. So it is desirable for a solvent to allow the use of common, relatively inexpensive material for construction at moderate temperatures and pressures. As long as it's being operated at moderate temperatures and pressures, we want as much as possible to use a solvent that will not use very expensive materials of construction for our equipment. Then availability and cost. I think in any project study, this is I think if it's second only. The first is safety, then second is the availability and the cost of the particular material to use. So it's really like immaterial to have a solvent having all the good properties but it's not available and it's very costly. So alternatives normally are in this case, being considered. That way the cost will not really hurt the overall process in terms of cost. So solvent should be readily available at a reasonable cost. Because class, if you're going to buy a solvent, let's say for example, it is imported, your inventory will also take cost. So letting that solvent come in will take time. So the plant will have to ensure that there is considerable amount, usually constant, in the inventory. So if it should remain, that particular amount should remain in the inventory, that will entail cost, money that is spent on that particular inventory until such time that replenishment from such solvent will come in from outside, from abroad. So that's really very important in terms of availability and cost. Now for these solvent properties, you can read more or you can complement what is being discussed here on section 15, that's 11 to 13 in your handbook, because the primary source of the material in this set of slides is your handbook, the Paris Chemical Engineer's Handbook. Now, if we do calculation and extraction, normally there are three phases. Actually, in all cases, there are three phases to components rather that are being considered. The three components are A, B, and C. And these components may be present in all your phases, or maybe only one component in one particular phase, but we only have the presence of these three components in all four phases. The four phases I'm referring to is the feed, the solvent, the extract, and the raffinate. Now, the A is your solute. Solute. The C is the solvent. It is the extractant, the main component in your solvent that is responsible in separating A from its carrier solvent in the feed. And the B, most of the time, is water. Water, which is the carrier solvent of A in the feed, or it could also be incorporated with your solvent in your solvent phase. So we only have three components: the solute, the water, and the solvent in your extraction. Now, variables to consider here in extraction is temperature, pressure, and concentration. So these three will have major roles later in the effectiveness of the extraction process. Now you see this XA plus XB plus XC equal to 1. This means that the concentrations of A, B, and C in the feed or in the raffinate, because it's X, should always be equal to 1. I did not write anymore here the Y. YA plus YB plus YC should also be equal to 1. What is Y? That's the concentration of the solute or of B or of the solvent in the solvent phase or in the extract phase. So concentration in the feed and in the raffinate are represented as X. Concentration in the solvent and in the extract are represented as Y. It's using appropriate subscripts A, B, and C as to pertain to a particular concentration of that particular component. So if it's A, then it's XA or YA. So that's how we represent concentrations here in extraction. Now, in an extraction unit, we have this what we call equilibrium data extraction from a triangular diagram. This is not often used, but it's important that you understand how you're going to read the concentration of, let's say, for example, a particular mixture having A, B, and C. Or shall we say, how will you determine or read out the concentration of the bulk phase M? The bulk phase M is the phase resulting from the mixing of your feed and your solvent. When your feed phase and your solvent phase mixes already, it will form the bulk phase M. And we are interested in determining the concentration of A, B, and C in this bulk phase M. How would you be able to read that in this equilibrium triangular diagram? It's actually very easy. On the horizontal axis here of your triangle, you're trying to get the concentration of B. And that's water most of the case. So 0 concentration here, and then you have 100 concentration here of water. And the way you read it is parallel to the mass fraction of A in this left side of your triangle. The left side of your triangle. So you read in this manner. So it's 0.2 for B if it's in here. If your M is here, that would be 0.4, 0.6, 0.8, and 1.0 for B. Now, if you want to determine the amount of C in your bulk phase, and that's your solvent, is easy because you have to read it parallel to this particular axis. So C is read through this side of your triangle, the right side. So parallel to the horizontal axis, so you have 0.2 and 0.4. So it tells you that the bulk phase M has 0.4 in terms of the mass fraction of C, and that's the concentration of C in the bulk phase. So you have here 0 and you have here 1.0 for C. Now the left side, I already mentioned a while ago, gives you the concentration of the solute A. So it's 0 here and 1.0 down here. So that's how you read through the concentration of A in your bulk phase. So how you read, it's parallel to the right side. Okay, 0.2. So in this case, your A in the bulk phase M is 0.4. Actually, class, if you know A and C, you need not read B. Or if you know A and B, you need not read C, because the sum of these three should be equal to 1 as pointed out in the previous slide. Okay, so this is how you read the concentration of the bulk phase M on the equilibrium triangular diagram. Now, there are this triangular diagram which has, shall I say, partially miscible components only. Like in this case, your component, let's say for example, your component A is only partially miscible with the B or with the C. So how would you write particularly that particular triangular diagram in triangular form? So in this case, you have, shall I say, a one phase region here. It's so easy to tell actually. You have your one phase region here and your two phase region here. In here you have one homogeneous phase. As such, it's called one phase region. In here you have a two phase region. The reason why you have a two phase region because you have partially miscible components, meaning not all components A, B, and C are completely miscible with each other. There are components which are only partially miscible with each other. So in this case, you will have this particular region consisting of the two phases that are not completely mixed and this particular region which is completely mixed. This is the tie line. So we'll be talking about the tie line later when I will discuss to you the graphical approach of solving problem and extraction. This is the plate point B. So nonetheless, this is how it would look like if you have partially miscible components in your extraction. Now read through section 15-26 in your handbook for this and refer to figure 15-18. So your diagram for partially miscible components will have a two-phase region and a one-phase region separated by what we call this phase envelope. Refer to this curve as the phase envelope. Now, if we go back to the other triangular diagram, this one, your components are completely miscible. So you don't have the formation of immiscible phases. In here, you have components completely miscible with each other. This one, you have partially miscible components only. Now, there is this particular diagram and it's unique about extraction only. It does not happen. You can't find this particular equilibrium diagram in other separation processes, only in extraction. It's because what's unique about it is it has two diagrams connected to each other, or one will not exist without the other if the solution to the problem will be treated as purely graphical or will be treated with some graphical interpretations. Now, in that particular set of diagram, you will be needing example for the liquid-liquid equilibrium data, in this case of acetone, water, methyl isobutyl ketone system. So water is the B, acetone is the A, and MIK is your C. Your solvent is MIK. So you have these two sets of data all written in one table. So you have the acetone distribution in the water phase and in the MIK phase. I'd like to explain the water phase is the raffinate phase and the MIK phase or the solvent phase is the extract phase. This is to be treated as one set. Whereas in here you have three columns and this will be used in constructing another graphical interpretation. This will have another graphical interpretation that goes along with this. And in here you have the composition data of acetone, water, and MIK in the system. So in it, this is for the phases, the two phases, product phases of extraction. How is this table to be interpreted or translated rather into an equilibrium data that are connected or linked together? One will not exist without the other. And by the way, class, this is only true, this data is only true for this system. We change the system, we change what the data in here. And this is empirically determined. So this data actually is interpreted or translated in terms of this diagram. If you look closer at the bottom of this diagram, you have the water layer composition and you have the ether layer composition. So meaning this is the water-rich phase and this is the solvent-rich phase. In constructing the curve that you are seeing here, anyway, the 45-degree line is just drawn because it's a 45-degree line, slope equal to 1. The curve here is constructed based on the data that you have on the leftmost part of the table here. The last two columns represent the X and the Y that will be plotted to give you this rectangular equilibrium data that goes with this triangular data. Okay, this is how you interpret the last two columns in the table. Now, the other three in this table is resorting to this upper triangular diagram, the triangular diagram that you are seeing here. So you have in this diagram the two-phase region, the region wherein you have two phases present, and you have the one-phase region wherein you only have one homogeneous phase present. It's being separated by this phase envelope. Now, how do you construct this phase envelope? In the same manner that you know already how to construct this curve, this equilibrium curve, using the last two columns. This phase envelope class is constructed using the XA and the Y, the XA and the XC in the data that you are provided in the table in the previous slide. So you have actually on the horizontal axis of this triangular diagram either XA or YA, but it pertains to the concentration of A. So you have the concentration of A. And in here on the vertical axis, you have the C, the concentration of the solvent. Nowhere can you find B because B is in here. It's water. So again, the horizontal axis is for your solute. The vertical axis is for the C. How do you construct this one? You use the A and the C concentration in the table here. So the C composition is for the MIK. So this is your MIK. And your A composition is for the acetone. If I may say, we are not using the third column in here in constructing the phase envelope in that upper triangular diagram. We are only using the first two columns, the MIK column and the acetone column. MIK for Y, acetone for the X. That way, we can construct this phase envelope. We need these two diagrams so as we can treat accurately, graphically, problems related to extraction. Some of the problems are to be solved both using graphical, you are to extract information from the graph, and analytical procedures. In analytical procedures, we're only using pure material balance. In graphical, we're using simultaneously the construction of the lines and the points that we have placed in here together with, so we use the data we're getting here together with the material balance equation. That way we can come up with the required information of the problem. Now I will illustrate that, the use of this diagram in the case of a sample problem. You have a similar sample problem to that found in your handbook in John Couples because it's based from John Couples, and that particular problem is example 12.5-1 if you're using the Philippine edition for John Couples. So, sample problem 12.5-1. In this case, I have changed the data just for illustration purposes. So you are given a mixture weighing 200 grams. And in this 200 grams, it has 50 isopropyl ether, 20 acetic acid, and 130 water. So it's all already well represented here in terms of A, B, and C. This particular mixture is to be equilibrated in a mixer settler, and later on, after phases have been already formed, and that is the raffinate and extract phases, we would like to separate them. So How do we determine the compositions of the raffinate and extract layers in this case? You are only given a mixture that is equilibrated, and we expect after some time, when equilibrium is reached, that it will be forming these two separate layers, the extract and the raffinate layers. We intend to know the composition of the extract and the raffinate layer in this case. So how do we go about determining that? So remember, so you have 50 for isopropyl ether, 20 for acetic acid, and the rest is water. So C is 50 and A is acetic acid. So it's very simple actually, class, how to treat this particular problem. So what you're going to do is just determine the composition first, of your bulk phase. So it's the bulk phase composition that you are interested in knowing. So we will determine the composition of that bulk phase. And that bulk phase will be letter M. So we want to determine the composition of bulk phase M. So that composition would be XAM. XAM is the composition of your solute in the bulk phase. In the problem, we know that our A there, so I memorized it already so we don't need to transfer slide. Your M there is, or rather your A there is equal to 30, if I'm not mistaken. So is it 30? We divide it by the total amount of mixture that we have. So we have 130 for the solvent, we have 50, and we have 130, so I think it's 20. So wait, it's 20, it's not 30. So we're going to change that. We're going to change this to 20. So you have 20 here. So that's for your A. We'll go back to later on to the problem to check if it's really 20. I forgot. So we'll check if it's really 20. So we won't have to keep on repeating. So our A is 20. So we go back to what we're doing here. And 20 divided by 200, that would be a 0.10. So that's for your XAM. You only need the A and the C. Then you've determined the XCM. So we know from what we read that it's 50 and the total mixture mass is 200. So that would be 50 over 200, so that would be 0.25. Okay, so you have already the composition of the bulk phase. What you're going to do, you go back to triangular diagram. So I'll draw here a triangular diagram similar to what was shown to you a while ago. So you should have a triangle, and you should have a rectangle here. And let's say you have this phase envelope. Okay. For now, for this problem, we won't do the plotting because it will take time. Let's say, for example, you already know how to do this. You already know how to draw the equilibrium curve and the phase envelope in the upper part of the diagram. So I'll draw the curve here below. So this is just an approximation. So based on what we have there in the data in the first slide, so this is 0.10 for A, 0.25 for C. You're going to plot that in your upper triangular diagram. So 0.2, 0.10, and 0.2. So let's say I forgot. So 0.10 for A, 0.25 for C. So let's say, I'll change the color of this one. Okay, we'll find the 0.10 somewhere here, and the point C, which is 0.25, I'll have it here. So this is, let's say, wait, I cannot draw it properly. So that's your bulk phase M. That's your bulk phase M. And we're going to construct what we call the tie line that will pinpoint to us the location of the raffinate and the extract layer. By the way, class, when we speak of the extract layer, it's here on the upper part of the face envelope that you can see the extract. The raffinate is written here below. So the process of determining the composition of the extract and the raffinate layer here is really graphical, and it's trial and error. Now, I don't want to miss this one just because it's not going to come out of the board exam. I just want to teach you this, and later on I will leave you to your own readings to complement what I am discussing here. So what you're going to do in this case is, let's say, I'll get another color here. Another color, let's say, what did I not use? Green. Okay, let's say I will try checking whether this is the appropriate point for my raffinate. Let's say this point here is my raffinate. What I'll do, I'll go down until I reach the curve. That's the first procedure. Then I go left until I reach the line. That's the second procedure. Then I go up until I reach this part. Okay. The points that I have placed here is my first trial for the raffinate, and this one is for the extract. How do I know whether the tie line that I have established here, the tie line would be this one, this line? Wait, Kasan. What color have I not used? Black. Okay, the tie line would be this line that's supposed to pass through the yellow and the R. And just make it pass so that we won't have any tie anymore. So if I will connect E, in this case, if I will connect point E to R, after I have done the construction of this we call these lines, and if it will pass through the bulk face M, let's say this is my bulk face M, then this is the R and the E. What you're going to do is read the A here and read the C here. That would be the composition of your raffinate layer. For the extract layer, you read the A here and you read the C here. That would be the composition of your extract layer. For you to know B, all you have to do is get the sum of the A and the C and then subtract it from 1. That would give you the B. The reading for the composition here is your extract composition. So extract will be having composition Y because it's extract, YA and YC. Your YB will be just 1 minus YA plus YC. Now the same thing with the raffinate. So your composition for the raffinate would be XA and XC. Your XB will be 1 minus XA plus XC. So this is what I meant a while ago when I was pointing out to you in the shall I say, in the illustration in the PowerPoint, that the composition will only need 2, and you only get to get the sum of the 2, subtract it from 1 to get the third component composition. Now this one allows you to graphically, just given only the composition of the bulk phase, actually it's not given, you computed it here, so to determine the composition of the raffinate and the extract layer after the mixture was equilibrated, and how the two separate equilibrium data was linked so that we'll be able to get this particular composition that we are interested in. So it's very graphical in interpretation. So in terms of the problem, if you go back to the problem that we were discussing here, you can now determine the composition of the raffinate and the extract layer using that particular procedure. Okay? Now, there's another problem related to this, and I'd like to end with that because it's already 1 hour after I've started recordings. It's like we're having a class, only the difference here is there's no interaction. I'm talking to myself. Anyway, There's another problem related to sample problem number 1 that we will be discussing, then we will end with that. Now, there are also cases, class, wherein your liquid pairs are partially miscible. So, the diagram that was shown here is for components that are partially miscible. It's the components that are partially miscible. What if you have the formation of faces already which are partially miscible? So your face envelope is somehow broken. You have a broken face envelope and you have two one-face regions. One at the upper part of the triangle, one and at the lower part. And you have also the tie lines here. So this is a sample of a phase diagram where for solvents B and C and A and C which are partially miscible. So B is only miscible to C, is only dissolved by C, same thing with A, only dissolved by C. But A and B are not miscible, so it forms two partially miscible phases, and in that case your diagram would be looking like this. So an equilibrium diagram for a partially miscible liquid pairs. I leave to you as an assignment how to read on how is this particular diagram to be interpreted and to be understood for partially miscible liquid pairs, and for this one with partially miscible components. You should be able to distinguish one over the other. If you don't have any resources for that, let me know. I will give you the resources for you to read. Give you resources for that. Although, and I will take this as an announcement, there's already a resource, a library resource incorporated in our Canvas where you can access library, shall I say, materials for you to use that will come in handy in this COVID season wherein you cannot go into the library. I will post that particular thing in the announcement later. So we have also the inverse lever arm rule here. In the inverse lever arm rule, you can determine the amount of the bulk phase or any of these two phases knowing only the two. And in that, the interpretation is also graphical. So graphical in the sense that you plot L, the feed, using its composition A and C on the triangular diagram. The triangular diagram that I'm referring to would be this diagram. This one only. So you plot the L here using the A and the C composition for your feed. That's the same thing with the That's the same through with the solvent. So for solvent, you plot A and C, but look at the way it's labeled is Y. For the feed, it's labeled as X. For the bulk phase, you have it labeled as X also, but it will have A, M, and CM to specify that that's the composition of the bulk phase. So this is how we use the inverse lever arm rule. It's actually ratio and proportion. If you want to determine the ratio of L to V, what you're going to get is, if it's L to V, you're going to get this length here. It should be V to, or rather M to V. If it's V, it should be L to M. So it's inverse because I'm trying to determine the value of L, but the one that I'm measuring is for the V from the M, so that should be VM. If it's V, that should be LM. But if it's M, that will be LV. That's in the inverse lever arm rule. And you can find that also in John Couples and how you're going to interpret this particular graphical representation of the inverse lever arm rule, and it will be illustrated also in the next sample problem together with the answer. Okay, so we go to the next sample problem. It's a continuation of sample problem number 1, and I'd like to end with this. So let's say, for example, you already determined the composition of the extract layer in sample problem number 1, and the answers are this. This is just an example, and that for the raffinate, these are the values also of the composition. The original mixture contained 100 kilograms and XAM is equal to 0.10. So take note. You know that already that these are the compositions of your extract, and these are the composition of your raffinate. The excess are for your raffinate. And in this case, in the same treatment as number 1, although number 1 is not originally 100, it's 200. What I'm trying to say in this here is the treatment in determining the composition is the same as sample problem number 1 on how to get the values of the composition for the extract and the raffinate layer. So what you're going to do is make use of this information and determine the amount of V and L. So we will go to from this slide to the other slide later. We'll go to our drawing board so we can have the material balance. In that case, in our problem, if you do material balance, if you do overall material balance in that problem, so you have L, the feed, plus the solvent is equal to the bulk phase M. Okay, in that problem. So we know that this bulk phase M is equal to 200. So you have to know that in here, you are to determine the amounts of the V and the L. So it's the thing that we're trying to look for. So we go back to what we're doing there. We are trying to find this. So from this particular material balance, you will have L equal to 200 minus V. So we can have this as our equation 1. Then you can do component balance. So in that case, you will have LXA plus BYA equal to MXAM. I'm trying to make a component balance on the solute because most of the time class it's suggested that you do component balance on the solute. Since you do not know the L, that would be, let's say, a 200 minus V, and you will have XA. The XA is the XA that is given in the problem, which you determined using the graphical approach in sample problem number 1. So your XA here is 0.12. So we go to substituting 0.12 here. And you have the V, and your YA is 0.04. And you have 200, and your XAM, which is 0.10, if I recall properly. So you have 0.10. Yes, it's 0.10. So that in that case, you have only V here as the unknown. So you have the V, you'll get the V, and you have then the L. If you just substitute the V in here. So I'll leave that to you. You determine the V, and then you will have the L. And that already answers the sample problem here. Okay. However, class, you cannot answer this sample problem unless you have already done the graphical trial and error procedure illustrated in sample problem number 1. So it's important that you know how to determine the composition of the extract and raffinate layers graphically by trial and error before you use it together with the material balance equation in determining the amounts of V and L. Now, as to the lever arm approach in this case, as to the inverse lever arm approach, and if you're going to use the inverse lever arm approach, let's say you have this triangle again, sample, and you have already placed in here the L and the M and the V and the L, just like the way it's drawn in the PowerPoint. So this is your, let's say for example, this is your V and this is your L. Question, how did you plot L and V? You use the, for this feed, you use the XA and the XC. XA and XC, you have this point. For this solvent, you use the YA and the YC, so you have that. And what you do, since you're given already the composition of the M, which is 0.10, you locate the 0.10 here. For example, class, this is 0.10, but this is not 0.10 based on my drawing. And you just simply place it there, project it up until you reach the line, which is 0.M. That's your 0.M. Then what you're going to do is use ratio and proportion in determining the L and the V. So you can have L over M, for example, is equal to. So you get this one. If it's L, then I must be referring to V. So I will get this one and this one. So I will get Y, sorry, it's not Y because it's M, so it should be X because we represent the composition of the M using X. So this should be, okay. So this should be I'm referring to this because it's L, so it should be this one that I'm going to get. So this is X, sorry, I'm on eraser mode. So this is X CM minus Y C because this is X CM and this is Y C. The M will be this, so I will add here X C for the feed. So you have this one XC minus this one YC. So for the M, it's the entire thing, but for the L, it should be the other one. So inverse lever arm rule. Not that this one, but rather this one. Now, since you know already the values of this, you can read the C here of the M. Whatever is the value, you place it in here. The C, the XC, and the YC, you know it's given already. So you just place in the value given in the PowerPoint. This is over 100. You'll be getting L. That's using inverse lever arm rule. You have values here already, read from the diagram that you have or from the PowerPoint. In the case of M, you have to read it because in the PowerPoint, in the problem, it's only XAM that is given. Once you have the L, then you can determine the V. You just have to subtract it from the value of 100. That's how you determine the solution for sample problem number 2 using the inverse lever arm rule and using purely analytical approach. Now, your assignment will be posted in relation to the topics discussed within the day. I hope I won't be caught up by the brownout because there's a brownout here by 9 a.m. to 3 a.m. today. Okay, class, I will continue the rest of the topic on extraction after you are done with the asynchronous task that will be given to you today. I hope you enjoyed listening and hope there was learning through the ones that I have shared to you today. Okay, have a great day, class.